Hello friends, this video on aldehyde ketones and carboxylic acid part 9 is brought to you by examfear.com. No more fear from exam. Let's talk about some of the methods which are exclusively for aldehydes. They're only for aldehyde preparation. One is the method to prepare aldehyde from acyl chloride. Please know this is only for aldehyde. RCOH is the structure. One is from the acyl chlorides. Other is from nitriles and esters, and other is from hydrocarbons. From hydrocarbons, we'll talk about oxidation of methyl benzene by side chain chlorination followed by hydrolysis and by Gutterman-Koch reaction. So we'll talk about all these. First, let's talk about the acyl chloride. This is only for aldehyde. Please know, it's only for aldehydes. So in this we reduce acid chlorides, whatever this we have, right? We reduce it with hydrogen in the boiling xylene solvent in the presence of palladium catalyst, and we also use BaSO4. This is to poison. We'll discuss why we use this, right? So this is similar to hydrogenation actually. So if you see, we have discussed that we have this palladium metal and then we have hydrogen here, right? So this bond breaks and you have alkene. You can actually make it alkane using the similar process, right? So same thing applies here. You have some acyl chloride that is in the form of RCOCl. Here we use hydrogen in the presence of palladium catalyst and we use BaSO4 to poison it. I'll explain you why, right? And we use boiling xylene solvent, correct? So the mechanism is pretty same. You have this palladium catalyst, it's a metal, it's a the metal surface. This hydrogen bonds can easily break, and we can get H minus also. So what happens is in this palladium catalyst, hydrogen actually breaks into two of hydrogen free radicals, this one and this one, correct? Now what happens is, for example, I have this RCOCl, so this chlorine will easily be replaced by this hydrogen, correct? Why? One, chlorine is a good leaving group. Why? Cl minus is good leaving group. And the second, see, this is a lone pair repulsion. So this is the chlorine has lone pair here, oxygen has lone pair. So this is because of lone pair repulsion, because of lone pair repulsion between oxygen and chlorine, it is not that stable, right? So chlorine will leave and hydrogen will take its place. So you get this. And this is aldehyde. It's only for aldehyde, correct? So that is the mechanism, pretty easy mechanism. And now reason why we add BaSO4 is we want to poison it. We want to poison the surface, because if we don't poison the surface, this palladium attracts electron rich compound, right? So if you don't poison this, if you don't use BaSO4, what will happen is, I'll show you this. You have RCOCl, right? You do a reduction, it becomes RCOH. You do further reduction, it becomes RCH2OH, and then it becomes RCH3. So if you don't use palladium, if you don't poison it, what will happen is, this is a very strong reducing agent actually. This palladium surface, it will reduce my RCOCl, that's acyl chloride, to actually alkane. We don't want that, right? We want to stop it here. So with that, once you poison it, the capability of this palladium metal in presence of hydrogen to reduce the particular compound is less, right? So it can only do this much reduction. After that, it will not be capable of doing it, correct? So that is the reason why we poison it. If you don't poison it, the reduction will happen further and it will become alkane. You want to stop here, you want to stop here. To stop here, we need to poison. So the moment I'm saying poisoning, that means I'm making it weaker. A weaker, you can say making it a weaker reducing agent. Correct? So that is the purpose of barium sulfate, because this is a porous, it is a kind of porous metal, right? And if you put barium sulfate, this barium sulfate will sit in this holes and will make this whole metal less react. Correct? And this reaction is called Rosenman reaction. Rosenman reaction or Rosenman reduction. Rosenman's reaction or Rosenman's reduction also you can say. Correct? So example, if you want, I can take CH3 COCl, you add hydrogen in the presence of palladium catalyst BaSO4, right, to poison it, and again boiling xylene. So what you get is CH3 COH and you get HCl. What happens here is this H2 breaks into H dot and H dot. So one H dot replaces this, and what you Cl dot you get that reacts with H dot to forms HCl. Correct? Another reaction, if you want for aromatic, you have this compound. So in this also you add hydrogen in the same situation, BaSO4 and xylene. What you get is Cl is replaced with H and you get HCl, and this compound is benzaldehyde. We already know this compound. Correct? So we can easily prepare aldehyde from acyl chloride using Rosenman reaction. So one memory tip to remember this reaction is, see, Rosenman, rose in mind. That means your mind is full of rose, your mind is poisoned. Like you're thinking only about rose. Your mind is poison. And the moment you think about poison, there are only few reactions where we use this poison technique, right? So you can think of this reaction then that BaSO4 is used for poisoning. And then you can think of this reaction where you use acyl chloride and then use hydrogen, palladium catalyst and this poison to make sure that this is not very strong reducing agent, right? So you can think of this, just a memory tip to remember this Rosenman reaction. The next is we have to prepare aldehyde from nitriles. So there are various ways to do that. One is Rosenman reaction, Stephan reaction, where you use SnCl2 followed by hydrolysis. This is one. The next is we use diisobutyl aluminum hydride, that is AlHLi. And you have isobutyl here. This one, yeah. And then water. Two ways. Let's discuss the first one, the Stephan reaction. So here I have a nitrile. I use stannous chloride. Stannous and Stephan, the name matches, so it is a good memory tip to remember this SnCl2 to add with HCl. Some acid is required to form imine, and this on hydrolysis will give me aldehyde. So the reason why it works is, see, Sn plus 2, this is Sn plus 2, has tendency to go to Sn plus 4, right? So Sn plus 2 has some tendency to become Sn plus 4 due to inert pair effect. Since it has tendency to become Sn plus 2 to Sn plus 4, that means it has tendency to get oxidized itself. That means it is a good or mild reducing agent. So it is mild reducing agent. Correct? Why? Because it has some tendency to move from Sn plus 2 to Sn plus 4. Correct? So since it is a reducing agent, so reduction you can do either by adding hydrogen or removing oxygen. So here in case we'll add hydrogen. Correct? So if you see the reaction mechanism, I have Sn2 plus becomes Sn4 plus, it gives 2 electron, correct? So 2 electrons will be used by H plus from HCl to gives H minus. Now this H minus will react now. This H minus, what will happen is, suppose I have a nitrile group, I have R, C triple bond N. This nitrogen has a tendency, as more electronegative than carbon, so this nitrogen will get slightly negative charge, carbon will get slightly positive charge, and this H minus which we have will attack this carbon, right? So what you get is R, C double bond N minus. And H plus, there are so many H plus, everything happening in H plus solution, so this N minus will get one H plus. So what you get is R, C double bond N H. Correct. Now, since it is a mild reducing agent, it will not reduce the second double bond. Please note, since it is a mild reducing agent, it will not reduce the second double bond. It will not be RC, sorry, it is H here, yeah. It will not be RC H2 and H2. It will stop here. Correct. This is the max work done by Sn2. Correct. Now if you see, this nitrogen has lone pair. Now I am doing a hydrolysis. Correct. Now I'll do a hydrolysis. I am adding H3O plus, that is H plus and water. Correct. So the moment I do a hydrolysis and I am doing a adding water to it, what will happen is, this again, since it is having a lone pair, this will get attracted here and this bond will break. So what will I get is RCH with a positive charge and NH2. Correct. Now since I have added H plus and water also, so let me add water here. Water has a lone pair of electrons will get attracted towards this positive charge. Correct. So with this, what you get is RCH NH2 OHH, and oxygen will now get a positive charge. Correct. Conservation of charge. So electrons move from oxygen to carbon. Oxygen gets positive charge. Carbon gets negative. Negative and positive neutralize and forms a bond. This is what you will get. Now if you see, oxygen has a positive charge. Oxygen is an electronegative element. It won't like the positive charge. So it will give it charge out. How? This bond will break and it will become H plus, and H plus will go to NH3, right? Because nitrogen has a lone pair. Lone pair of electrons will attract this H plus. Correct. So this H plus will actually be attracted by this nitrogen. So what you get is RCH NH3 with a positive charge and OH. Correct. Now nitrogen also is electronegative element. It won't be happy with a positive charge. So what it will do? It will come out. It will come out in this fashion. The bond will break and this will come out, right? If the bond will break in this fashion, this will get negative charge with positive charge, negative positive neutralize, and NH3 is very happy out, and you will get a carbocation. NH3. Correct. Now carbon has a positive charge and we have hydrogen here, right? Now we have seen this so many times. Actually, I'll just draw like this. OH, yeah. We have seen this so many times. So what will happen in this case? Somebody has to leave, right? Or something has to come. But if you see, it's all H plus here. So what will happen here is this bond will break, right? This bond will break in this fashion. So what will happen is oxygen will get a negative charge. Carbon negative positive charge will form a bond. So you get RCH and here you form a double bond. And H plus comes out and it is in the system, right? Because we have a lot of H plus ions in the system. This is what you get as the out. Hope you remember this reaction. Let me repeat once again. So I have Sn plus 2. It has slight tendency to become Sn plus 4. So it's a mild reducing agent. Sn plus 2 becomes Sn plus 4, 2 electrons is used by H plus, you have a lot of H plus in the system to gives H minus. This H minus attack this RCN and you get this compound, right? And then this N minus will attack H plus from the system, you get this compound. Now, since it is a mild reducing agent, it won't reduce this further. Now on this, I am doing a hydrolysis. It is H plus and water, correct? So this H plus will attack this or this lone pair of electrons will attack this H plus because that's a good electron rich side. You get this, the bond breaks and carbon gets a positive charge. We also added water, so water has this, oxygen has the lone pair, it will attack this plus charge on carbon, you get this compound, and this nitrogen has a lone pair, it is okay to get some positive charge. This has a positive charge here, oxygen doesn't love positive charge, electronegative element, so this bond will break and H plus will join this guy, nitrogen. So now nitrogen gets a positive charge. Nitrogen doesn't like positive charge, again it's electronegative element. It comes out, the bond breaks. NH3 comes out, and NH3 is a good, it's a gas actually, it leaves very easily. So NH3 comes out and carbon gets a positive charge. Somebody has to leave. So this hydrogen says, okay, I'm leaving. Hydrogen leaves, oxygen gets a negative charge, carbon gets has a positive charge, positive and negative charge forms a double bond, and you get this aldehyde. This is the reaction mechanism. See, the next reaction we have is, as I told, you have RCN and you can just use this diisobutyl aluminum hydride. Isobutyl, yeah, and then you add water, you get RCOH. That is also one possibility. It is also a reducing agent, mild reducing agent. So here also you'll get the similar kind of stuffs, right? It's mild reducing agent, and then from here the reaction is almost same. So here also we use diisobutyl aluminum hydride, just we have discussed. Diisobutyl aluminum hydride. This is how we call it, and let me draw the structure for this because we have been using it quite frequently. This is the structure of diisobutyl aluminum hydride. This is 2 isobutyl, 1 aluminum and 1 hydride. This is the structure of diisobutyl aluminum hydride. This is a bulky reducing agent. It's a bulky. It's not strong reducing agent, it's a weak reducing agent actually. So if we use lithium aluminum LiAlH4, so it will, whatever aldehyde you get, it will be reduced to alcohol. So LiAlH4 is a very strong reducing agent. LiAlH4 is again a reducing agent, but it's a very strong. So we'll not be able to use it for aldehyde because the moment you get aldehydes, and since you have used LiAlH4, it will become alcohol, right? So we should not be using strong reducing agents. We have to use weak reducing agent, and diisobutyl aluminum hydride is one of the weak reducing agent. Correct. So here we do the same thing and we use low temperature, -70 degrees Celsius, and this is all reduction actually. So what we understand, we are doing a reduction by a weak reducing agent at a low temperature, right? So I have my, let's suppose, ester, right, and let me take a general equation now. This is my ester, and then I use again diisobutyl aluminum hydride first, and then do hydrolysis, right, in acidic medium. What I get is RCOH. This is what I'll get. So for example, I have, let's suppose, CH3, CH2, CH2, COOO, CH3. So in this case, I use DIBALH and then H2O in presence of H plus, I get CH3, CH2, CH2, COH. This is what I'll get. This is my aldehyde. Thank you. Visit our website examfear.com to watch more and more quality education videos. You can also attempt free online tests that are there in our website. You can also get access to tons of free study materials, and you can also find free tutors and mentors in this website. Thanks a lot for watching.